Swayam Prabha. Digital India. Educated India.
Welcome to the fourth lecture of the module on sliding contact bearing. Till this lecture, it means in the lecture number 1, 2 and 3, we studied about the introduction of the bearings, different type of bearings, and then the details about the sliding contact bearing, its nomenclature, its working principle, generation of hydrodynamic pressure, and mathematical modeling for determination of pressure profile which develops in the clearance space of a hydrodynamic bearing. That was determined till now. Thereafter, we also studied for the case of a bearing, what happens when bearing inside the bearing, lubricant with the temperature T1 goes inside and comes outside with the temperature T2, and through side leakage also the fluid comes out from the clearance space. Then the temperature balance or the enthalpy, through the enthalpy balance, we found the rise in temperature when the fluid moves from inlet to the outlet of the bearing. Now the next type of bearing, hydrodynamic bearing, which we will study, is the self-contained bearing, in which the lubricant not goes outside the clearance space, but there is a space, inside that space it is contained, and so it is called the self-contained bearing. Now the case in which the lubricant carries away all the enthalpy increase from the journal bushing pair has been studied in the previous class. The bearings in which the warm lubricant stays within the bearing housing will be addressed. These bearings are called self-contained bearings because the lubricant sump is within the bearing housing and the lubricant is cooled within the housing. This was the bearing we studied in our previous class, where the lubricant was supplied inside the clearance space at temperature T1 and with the flow rate Q. The lubricant was coming out from the clearance space in two ways. The first was through this outlet along the circumferential direction. This is the return, and the temperature at return will be equal to temperature at inlet plus rise in temperature during travel of the lubricant in the clearance space. And so the temperature will be T1, the inlet temperature, plus delta T, the rise in temperature. The flow rate which was coming in was Q. From this flow, some of the fluid is going out through the ends, that means through the axial direction, that is called the end leakage, and the flow rate through the ends is Qs. And so in the return, the amount of fluid which is coming out is flow in Q minus the side leakage Qs, and the temperature of the lubricant which is coming out through ends in the axial direction will be the inlet temperature T1 plus half of the rise in temperature delta T divided by 2. In this analysis, we had taken a sum where the lubricant was coming in and going out. So, from this sum, the lubricant was going to the clearance space and it was coming out as a return, and it was coming in the sum through the end leakage. So, in the control volume we had Q1 which is going out, Q and temperature T1, and Qs is coming at temperature T1 plus delta T divided by 2, and Q minus Qs is coming in the sump at temperature T1 plus delta T. Now, this is another type of bearing where there is no any sump, but inside the bearing itself there will be a space where lubricant will be there, it will not come out. In this particular case, there is a keyway type of sump inside the bearing, keyway sump, a slot is there, and in this slot the lubricant is stored. So, in this particular case, side leakage will be negligible. This is your journal shaft, journal or the shaft. The radial load is W. The radius of the shaft is R and the clearance is C, and the shaft is rotating with a speed n. Well, the keyway is shown here, that acts like a sump, and this figure is the sectional view of this one taken from AA. These bearings are described as pillow block or pedestal bearings. They find use in fans, blowers, pumps and motors. Integral to design consideration for these bearings is dissipating heat from the bearing housing to the surroundings at the same rate that enthalpy is being generated within the fluid film. Now, in this type of bearings, through the bearing housing itself, the heat will be dissipated, there will be loss of heat through convection and radiation, and the shaft is doing work on it when it is rotating, and due to that some heat is generated. Heat is generated. That generated heat, frictional work is your frictional coefficient of friction F multiplied by W, and the frictional torque Tf is Wf multiplied by radius of the shaft, that is radius of the shaft is R, and that is Fw R. So, knowing the coefficient of friction, which you may get from the graph drawn between Sommerfeld number and R by Cf for different L by D ratios. So, you can get F knowing the Sommerfeld number, and knowing the value of W and R, you will have this Tf, and heat generated will H is equal to 2 capital T small f then capital N. Now, in a self-contained bearing, the sump can be positioned as a keyway-like cavity in the bushing, the ends of the cavity not penetrating the end planes of the bushing. Film oil exists the annulus at about 1/2 of the relative peripheral speeds of the journal and bushing and slowly tumbles the sump lubricant mixing with the sump contents. Since the film in the top half of the cap has cavitated, it contributes essentially nothing to the support of the load, but it does contribute friction. Bearing caps are in use in which the keyway sump is expanded peripherally to encompass the top half of the bearing. This reduces friction for the same load, but the included angle beta of the bearing has been reduced to 180 degree. Charts for this case were included in the Raimondi and Boyd paper. The heat given up by the bearing housing may be estimated from the equation. That means the bearing housing in which the bearing is there and the shaft is there. Through this housing, the heat will be dissipated. So, heat given by bearing housing may be estimated from the equation Q loss is equal to UA within the bracket TB minus T infinity, where Q loss is the heat dissipated in watt, U is the overall heat transfer coefficient for radiation and convection. So, through radiation and convection, what amount of heat will be dissipated? For that, the combined overall heat transfer coefficient is given by U. A is the surface area of the bearing housing, because through that surface area heat will be dissipated. TB is the surface temperature of the housing. So, the housing temperature is TB, or you may say it the bearing surface temperature. Okay, and so subscript B is used. T infinity is the ambient temperature. So, the ambient temperature is T infinite. So, as this TB will be more than T infinite, heat will be dissipated from this surface. The overall heat transfer coefficient U depends on the material of the housing, the surface coating, geometry, the roughness. Even on the roughness it depends. The temperature difference between the housing and the surrounding objects, and the air velocity. Because if the air velocity is smaller, there will be natural convection, and if it is moving, then it will accelerate the dissipation. After Kyralids and others, in ordinary industrial environments, the overall heat transfer coefficient U can be obtained from this formula. In this, the overall heat transfer coefficient has 3 values corresponding to 3 conditions. The first is for the still air. Through the bearing housing, the air which is flowing is a still air. For shaft stirred air, it is 15.3 watt per meter square degree centigrade. For air moving at 2.5 meter per second, it is 33.4 watt per meter square degree centigrade. Now, there is a relationship between the fluid temperature, that means inside this bearing casing is the shaft, okay, and in the clearance space there is a lubricant, okay, and the lubricant temperature is high and that we want to dissipate, okay. So, the lubricant temperature is represented as Tf, and this is the required temperature because this temperature must be known because it will affect the viscosity of the lubricant, and from this temperature and the rise in temperature we will get the viscosity, and thus we will get the Sommerfeld number. So, this Tf, the fluid temperature, is an important term. So, Tf minus Tb, the bearing surface temperature, may be given as a constant multiplied by Tb minus T infinite. So, these two relations, these two can be related with these two with a factor alpha, where alpha is given by this table depending on the different lubrication systems. If oil ring is there or the oil bath is there, oil bath means you will have a bath and the lubricant is there and your bearing is inside this bath, okay. And oil ring means all along the circumference of the bearing an annular ring is there, and through that lubrication is done. So, depending on the lubrication system and the condition of air, either it is a moving air or a still air, we have the value range of the alpha. So, knowing the condition, knowing the lubrication system, we will get the value of alpha from this range of alpha. Well, so now you can relate your equation of Q loss with respect to this Tf and T infinite, because your Tf is the fluid temperature, Tb is the bearing temperature, and T infinity is the ambient temperature. So, we have Q dot is equal to U, the original formula is Q loss is equal to UA Tb minus T infinity. The overall heat transfer coefficient is given by these values, which is 11.3 watt per meter square per degree centigrade for still air, and it is 15.3 watt per meter square degree centigrade for shaft stilled air, and 33.4 watt per meter square degree centigrade for air moving at 2.5 meter per second. So, depending on the situation, we can select the overall heat transfer coefficient and we can find the Q dot loss is equal to UA, overall heat transfer coefficient. A is the casing area, the external area of the casing, and Tb, which is the this box temperature within which the bearing is kept, bearing system is there, minus T infinite, which is the ambient temperature. Well, now this can also be written in terms of the fluid film temperature Tf, where Tf is based on the average temperature, because we know that if the inlet temperature is Ti and the outlet temperature is Ti plus delta T from the bearing housing, then the temperature of the fluid inside the bearing will be the average of these two. So, this Tf is based on the T average, and this Tb, the block temperature, can be taken as uniform because this is usually made of metal and we can consider isothermal condition. Now, we have a relationship between the fluid film temperature, this Tf, and the housing temperature Tb is equal to alpha times the housing temperature or the block temperature Tb minus the infinity. And this alpha can be determined from this table based on the lubrication system, if it is of a oil ring and and depending on the condition of moving air or the still air, the range of alpha is 1.2 and half to 1. And if it is of oil bath type, that means the complete system is within the lubricant, the oil bath is there, then again corresponding to moving air and still air, we have a range of alpha. So, knowing the value of alpha, now we can write this equation in terms of the fluid temperature, which is based on the average temperature, and the atmospheric temperature. So, this Q loss will equal to UA, and in place of this TB minus T infinite, we can write the TF minus T infinite. So, TF minus T infinite is obtained from this equation, and from this equation we got TB is equal to this TB is equal to TF, the fluid temperature, minus alpha, the atmospheric temperature, divided by 1 plus alpha. And so, the heat loss rate can be obtained as UA, overall heat transfer coefficient, multiplied by the lateral area of the housing divided by 1 plus alpha obtained from this table, multiplied by the fluid film temperature minus the atmospheric temperature. In beginning a steady state analysis, the average film temperature is unknown, hence viscosity of the lubricant in a self-contained bearing is unknown, because we have seen that the Sommerfeld number is a function of mu, mu is a function of temperature. Now, the temperature of lubricant is not known to us. We have inlet temperature of the lubricant and the outlet temperature of the lubricant in the case of previously studied bearing where there was a sump. But for this self-contained bearing, that is not known to us, because the lubricant is inside the bearing, it is not coming in and going out, and so the average temperature of the lubricant is not known. So, T average from which we determined the value of mu in the previous bearing, this T average was taken as T1 plus delta T divided by 2, and this was the preliminary value of average temperature of the lubricant to get the Sommerfeld number. Now, this is not the case for the self-contained bearing. So, what we do is finding the equilibrium temperature is an iterative process wherein a trial average film temperature and the corresponding viscosity is used to compare the heat generation rate and the heat loss rate. So, in this case what we do is we just assume a value of average film temperature TF, okay, and from this TF we get the value of mu, and from that we get the value of Sommerfeld number, and then from this Sommerfeld number we get the coefficient of friction, and knowing the value of W, knowing the value of R, the shaft radius, we get the heat generation H in or heat gen dot, okay, and the heat which is required to dissipated is obtained from the equation just obtained, Q loss dot, which was in terms of UA and TB minus T infinite, and later on it was found in terms of TF also. So, this heat gen and heat loss are compared. Well, an adjustment is made to bring these two heat rates into agreement. That means we make changes in such a way that these two becomes almost same. That means the amount of heat which is generating, if the same amount of heat is dissipated from the bearing casing, then there will no rise in temperature of the lubricant. And whatever value of initial value of lubricant temperature TF is taken, that will govern the things. This can be done on paper with a tabular array to help adjust TF to achieve equality between heat generation and heat loss. One of the table is shown here, and that table is corresponding to a numerical problem in which first the trial temperature was taken as 190 Fahrenheit, and corresponding to that temperature the mu viscosity was obtained from the curve, this curve, mu versus temperature. So, knowing the temperature, you can get the value of this mu. Knowing the mu, we got the value of Sommerfeld number, and from that, knowing the Sommerfeld number, from the Biomondi chart of R by Cf versus Sommerfeld number for our bearing with a L by D ratio, we get this Fr by C. Knowing Fr by C, we have this coefficient of friction, and thus we can find the heat generation. Okay, and from the formula Q loss is equal to UA Tb minus Tf, we get the heat loss. Now, in the first trial, these two are not same. Generation is 49.5 and loss is 45, and so heat will is generating more and the heat loss is lesser, and so temperature of the lubricant will increase, and that will decrease the viscosity, and thus you may not get the stable behavior. So, the next trial value of temperature was taken as 195, and the corresponding values of mu, S, Fr by C, heat gen and heat loss are shown like this. Now, when the temperature is 195, then heat generation is lesser and heat loss is more, just opposite to the previous one. It means your suitable temperature is lying in between 190 to 195. Well, so by this hit and trial method, we get the appropriate temperature, and we will get the appropriate value of mu and the Sommerfeld number. So, the final Sommerfeld number which you will got will give you the performance parameters from the Raimondi and Boyd charts. Because of the shearing action, there is a uniformly distributed energy released in the lubricant that heats the lubricant as it works its way around the bearing. The temperature is uniform in the radial direction, but increases from the sump temperature Ts by an amount delta T during the lubricant pass. The existing lubricant mixes with the sump contents, being cooled to some temperature. The lubricant in the sump is cooled because the bushing and the housing metal are at a nearly uniform lower temperature because of heat losses by convection and radiation to the surrounding at the ambient temperature T infinite. So, it is saying about the thing, the housing temperature is Tb, this is T infinite, the fluid temperature is Tf, but the bushing and others are at lower temperature. Okay. In the usual configuration of such bearings, the bushing and housing metal temperature is approximately midway between the average film temperature. Tf is given by Ts plus delta T divided by 2, and the ambient temperature is T infinite. The heat generation rate T gen at steady state is equal to the work rate from the frictional torque Tf, and this Tf will be your F, W, W is the radial load which is acting, and R. Now, let us discuss about the clearance space and what is the effect of clearance space on the performance of a sliding contact bearing. This clearance is an important parameter, because if the clearance is bigger, then it will have some good and bad effect, and when it is very less, then also there are some good and bad effects. So, we have to make adjustment in such a way that we have optimal performance parameters. So, let us study in detail the clearance and its effect on the performance parameters. In designing a journal bearing for thick film lubrication, the engineer must select the grade of oil to be used together with suitable values for P, which is the unit bearing load, the speed of the journal or the shaft, radius of the shaft, clearance, and the length of the bearing. A poor selection of these or inadequate control of them during manufacture or in use may result in a film that is too thin, and so you may land up to this zone of the Mackey's diagram, this zone, which is the thin film lubrication or the boundary lubrication. That may cause the bearing to overheat and eventually fail. Furthermore, the radial clearance C is difficult to hold accurate during manufacture, and it may increase because of wear. What is the effect of an entire range of radial clearances expected in manufacture, and what will happen to the bearing performance if C increases because of wear? Most of these questions can be answered and the design optimized by plotting curves of the performance as functions of the quantities over which the designer has control. This is a schematic diagram showing the effect of radial clearance on different performance parameters, such as the outside temperature of the lubricant, the temperature of the lubricant which is coming out from the clearance space, minimum film thickness, flow rate, and the heat generation and heat loss. Okay. The Q will be the flow rate, H is the heat generation. So, a plot of some performance characteristics of the bearing for radial clearance of 0.0125 to 0.075 mm is shown here. The bearing outlet temperature is designated as T2. The bearings should be designed for the shaded zone because wear will move the operating point to the right. Let us see how. If the clearance is very tight, you are in this zone, then minimum film thickness is small, okay, and the small film thickness is not good. The meaning is you have, and through the line of center will be the minimum film thickness, okay. Now, if due to any reason it further decreases, then there will be metal to metal contact, and Trumpeller has given a value of a minimum value of H0. So, you cannot decrease this H0 beyond certain value, okay. So, if the clearance is tight, then the value of H0 is lesser. So, you cannot make the clearance in this zone. Now with the increase in clearance, what is going on? As the clearance is increased, there is the gap between journal and bearing is increased. It is obvious that flow rate will increase. The flow of lubricant will increase, and this is shown by this curve. With the increase in clearance, the value of Q is increasing. What will be the effect on heat generation? Okay, when the clearance is lesser, then minimum film thickness is lesser, and this H is more heat will be generated. Okay, more heat will be generated because this space is lesser, and the fluid is to be moved from this bigger area to a smaller area, and this area is becoming is very less, and so more and more work has to be done. And so for a smaller clearance, heat generation is more, and with the increase in clearance, as flow rate is increasing, it will take away the heat generated, and so heat generation is coming down. The outlet temperature with the smaller clearance is lesser, is very high, and with the increase in clearance, as flow rate is increasing and heat generation is decreasing, this temperature will come down, outlet temperature of the lubricant. So where to put the operating point, or where should be our radial clearance? You see, the value of H is increasing with the increase in C, but beyond certain value it starts decreasing. So you cannot make a bigger clearance to get lesser heat generation and a small value of outlet temperature of the lubricant and more flow rate. That you cannot do. So suppose you are putting your clearance at this value to achieve the maximum fluid film thickness, then what will happen? Due to wear and tear, the clearance may increase, and with the increase in clearance, your H will decrease, and that may culminate to failure of the bearing. So what we do is, we make the range of our operating clearance in such a way that with the wear, if the clearance is increasing, then we are not landing to the zone where H0 starts decreasing. So our range will be to the left of this. So that range is shown by this colored area. Okay, in this colored zone, if you will be you have selected your clearance C, then with the increase in clearance due to any reason, maybe the wear, the H0 will increase, but it will not decrease. Okay. Now, figure in the previous slide shows the results obtained when the performance of a particular bearing is calculated for a whole range of radial clearances and is plotted with clearance as the independent variable. The bearing used for this graph is the one of the SA20 oil at the inlet temperature of 38 degrees centigrade. The graph shows that if the clearance is too tight, the temperature will be too high and the minimum film thickness too low. High temperatures may cause the bearing to fail by fatigue. If the oil film is too thin, dirt particles may be unable to pass without scoring or may embedded themselves in the bearing. The meaning is, if the gap is very small, then if some foreign particle is there, then it may embed in it or it may wear the surface. But if the gap is more, the lubricant flow will be more and the foreign particle will be flushed out. In either event, there will be excessive wear and the friction resulting in high temperatures and possible seizing of the bearing. This table shows us the clearance, what should be the average and the minimum clearance and the maximum for different type of fit. Now, close running fit, which is represented by H8/F7, okay, the tolerance levels, and for free running the symbol is H9, capital H9 divided by D9, the tolerance level for the shaft and the bearing. Now, this is shown here. It is maximum, minimum and average clearances for 1.5 inch diameter journal bearings based on type of fit. Now, this graph or this table is showing the performance of 1.5 inch diameter journal bearing with various clearances. With you see, the clearance is increasing in this direction, and with the increase in clearance, the T2 is earlier very high, 226 Fahrenheit, and it is reducing, and that was shown in the graph also. The H0 is increasing, but it is increasing up to this one and then starts decreasing. Coefficient of friction is decreasing, Q will increase, H will decrease. Now, this table shows you the possible bearing pressure. Possible bearing pressure means the value of P, the unit bearing load, that is W divided by LD. For different applications, what would be the range of this P? For diesel engines, main bearing, this is the range. For crank pin, this is the range. For Gaussian pin, this is the range. For automotive engines, main bearing, this one, crank pin, this one. For air compressor, this one. So, for different applications, you may find the range of the unit bearing load. So, from your application, if you have obtained, if you have selected a particular value of L and the D is fixed, so you must check whether your P is coming within this range or not. Now, the startup load, that means during the startup, what should be the load? The unit bearing pressure for starting conditions should not exceed 2 Newton per mm square or 2 megapascal. That means the static load W static divided by LD should be less than the 2 megapascal, and this was given by Trumpler also. The startup load is the static load when the shaft is stationary. It mainly consists of the dead weight of the shaft and its attachments. The startup load can be used to determine the minimum length of the bearing on the basis of starting conditions. The radial clearance should be small to provide the necessary velocity gradient. However, this requires costly finishing operations, rigid mountings of the bearing assembly, and clean lubricating oil without any foreign particles. This increases the initial and maintenance cost. The practical value of radial clearance is 0.001 mm per mm of the journal radius, that is, C should be 0.001 times radius of the journal or the shaft. And for different bearing material, the babbitt or the copper lead or aluminum alloy, the range of radial clearance is given in terms of radius of the journal in this table. Minimum oil film thickness. The surface finish of the journal and the bearing is governed by the value of the minimum oil film thickness selected by the designer and vice versa. There is a lower limit for the minimum oil film thickness below which metal to metal contact occurs and the hydrodynamic film breaks. This lower limit is given by this one. This should be checked with the Trumpler's criteria. For different L by D ratio, the value of H0 by C for maximum load and H0 by C for minimum friction. These are the two criteria for H0 by C. If you want to design your bearing for maximum load, then H0 by C for different L by D ratios will be selected from this column. But if you want to design your bearing for minimum friction, where low amount of heat should be generated, then you will select the H0 by C from this one. The Raimondi and Boyd chart also gives two dotted curves corresponding to the maximum load and the minimum friction. Maximum oil film temperature. The lubricating oil tends to oxide when the operating temperature exceeds 120 degrees centigrade. Also, the surface of Babbitt bearing tends to soften at 125 degree for bearing pressure of 7 megapascal and at 190 degree centigrade for bearing pressure of 1.4 megapascal. Therefore, the operating temperature should be kept within these limits. In general, the limiting temperature is 90 degree for bearing made of Babbitts. This figure can also be used for selection of the temperature based on the life. The figure can be used to estimate an upper limit when the characteristics of the application are known. Now, let us see one example for the self-contained bearing, and we will see how the initial fluid film temperature is selected, and by comparing the heat generation and heat loss, the final value of film temperature and the Sommerfeld number is determined. So, let us see this problem. It is, consider a pillow block bearing. Let us see a numerical problem for a self-contained bearing, so that we may know how to select a fluid film temperature, initially the trial temperature, and by comparing the heat generation and heat loss, we will get the final temperature, and based on that we will get the Sommerfeld number and other performance parameter. So, let us see how that is done. The problem is, consider a pillow block bearing with a keyway sump whose journal rotates at 15 rpm. So, the rotation of the journal N is 50 rps, revolution per second, not minute, in shaft stirred air. So, this condition will give you the value of overall heat transfer coefficient. Okay. The lubricating condition is shaft stirred air at 21 degree centigrade. Okay. With alpha is equal to 1, alpha is equal to 1, the lateral area of the bearing is 27800 mm square. The lateral area, to get the value of Q dot loss, it is UA and TB minus T infinite, and so lateral area is given by 25800 mm square. The lubricant is SAE grade 20. So, SAE 20 lubricating oil is used. The gravity radial load is 450 Newton. It means W is 450 Newton, and the L by D ratio is unity. In this particular problem, L by D ratio is 1. The bearing has a journal diameter of 50.000 plus minus 0.000. The tolerance level is given plus minus 0 and minus 0.050 mm, and bushing bore of 50.05 plus minus 0.1 oblique minus 0.00. Now, from this information, what will you get is, you will get the inside diameter of the bushing and outside diameter of the shaft, considering the upper and lower limit of tolerances. Well, so you have to find for a minimum clearance assembly, estimate the steady state temperatures as well as minimum film thickness and coefficient of friction. Repeat part A for a radial load of 900 Newton. So, initially the load was taken as 450, later on in the part B the load is to be taken 900. So, the effect of increase of load is also to be determined. So, the least radius clearance C is the C minimum and equal to 50.5. This is the inside diameter of the bush considering the tolerance minus 50.000 divided by 2, and that will give you the clearance. The unit bearing load is W is your 450, L by D is taken as 1 and L by D is 1, and the diameter of the shaft is given, one thing was given, yes, diameter of the shaft is here, okay, through which you determine the clearance. So, that is 50 is the diameter of the shaft here, this is your diameter of the shaft, this is the minimum diameter of the bush considering the tolerance capital D. So, if small d is 50, so L will be 50 and L multiplied by D is 50 multiplied by 50. So, P is 0.18 megapascal unit bearing load. Okay. Now, what you have to do is you have to find the Sommerfeld number, and Sommerfeld number depends on the viscosity, which is not known to us, and so we are determining the Sommerfeld number in terms of the viscosity, substituting the other known terms. R is known, C is known, N is known, P is known. So, Sommerfeld number is 83.3 mu. So, knowing the Sommerfeld number, we will get the RC by F, no, this term, the coefficient of friction R by Cf from the Biomondi and Boyd chart corresponding to this R by C and Sommerfeld number. Okay. So, the heat generation, this frictional power will be given by 2 pi the F, WR and N. Okay. This FWR is actually the frictional torque, okay, TR. So, the work done by friction WF will be 2 pi N, and that is this one, FR by C is written here. So, it means the heat generation which is equal to HF is now given in terms of FR by C. It is 1.06, this one in watt. Now, the rate of heat loss to the environment will be Q loss, and the formula for that is UA, overall heat transfer coefficient, lateral area of the bearing surface, alpha plus 1, fluid temperature minus the ambient temperature. So, fluid temperature is not known, ambient temperature was given, U is given, A is given, alpha is given, and so Q loss is determined in terms of temperature of the fluid, means mean temperature of the average temperature of the lubricant. So, we have a equation of this heat gen, and we have a equation for heat loss, and that we have to equate so that we may get a same value. Now, the unknowns are here. So, to get the Q loss, we must have a value of TF. So, a trial value of TF will be taken. taking the trial value of TF will give us the value of mu. Knowing the mu, we will get the Sommerfeld number, and thus we will get the value of FR by C. So, the trial value is this TF, and that is taken here. So, trial TF gives us mu dash, viscosity, it gives Sommerfeld number, and then we get the FR by C from this chart, and Q gen and Q loss can be calculated. And we found that heat generation is more than the heat loss. So, what we have to do is, we have to decrease the heat generation. Now, heat generation will be decreased if we have a lesser value of this, and lesser value of this we will get for the lesser value of Sommerfeld number, and for that a lesser value of mu is required, okay. And for lesser value of mu, temperature should be more, okay, because the relation between temperature and mu is something like this. We want lesser value of mu, and so temperature will be more. So, we are increasing the trial temperature to 90 degree. When we increase trial temperature to 90, we found that Q gen is 12.08, but Q loss is 13.5. It is just opposite to the previous one. It means the temperature at which these two will be same will lie in between 85 and 90. And you can do it in this tabular way to get the TF, which will give us the same value, and that is obtained as 88.4 degree centigrade, and for that both Q gen and Q loss are 13.27 watt. So, rounding off this, we are taking the TF, the temperature of the lubricant or the average temperature of the lubricant, as 88, and the corresponding value of mu is this one, and the corresponding value of Sommerfeld number is this one. So, the Sommerfeld number is taken as this one. So, this is the Sommerfeld number final, and corresponding to this Sommerfeld number, we have to find the other terms. So, 0.120 delta T by P is the chart. We have this chart 0.120 delta T divided by P, okay, versus Sommerfeld number. Well, so with help of this, delta T is obtained, corresponding to this Sommerfeld number, we get the delta T and the corresponding to L by D. From that, the inlet temperature or some temperature is obtained. Inlet temperature is equal to average temperature, because the average temperature of the lubricant AV is equal to T1 plus delta T divided by 2. This T average was the TF that we obtained here. So, TF is T1 plus delta T divided by 2, and so inlet temperature will be TF minus delta T divided by 2. So, this is obtained. So, T maximum will be Ti minus delta T and plus delta T, and that is 91 degree centigrade, and that is within the limit. So, then we get the TB. Now, after getting the final Sommerfeld number, now our aim will be to determine the performance parameters. So, we will come to the minimum film thickness chart, H0, chart, and we will get that corresponding to this Sommerfeld number, and we will check whether it is within our acceptable range or not, as per the Trumpler or as per the in the previous slide we studied. So, we have this H0 by C curve, and the Sommerfeld number is 0.62. So, we will be 0.6, this is 0.7, this is 0.6, 0.8 is somewhere here, and this is 1. So, 0.7 will be somewhere here. So 0.62 will be very much vicinity to this 0.6. So let's take this 0.6 for a time being, and L by D ratio is 1. So we'll go to like this 1, and this will be somewhere here. So H0 by C will be 0.7, then 0.7, 1, 2, 3, 4, 5, 6, 8, 0.78, 0.78. We have C, we have already calculated the C, and so we will get the value of H0. So H0 is obtained here, 0.78 multiplied by C is 0.02, so we have this one. Now what is the minimum value of this H0 as per the Trumpler? It is given in terms of the radius of the journal. So that we have to check it. Then position of the minimum film thickness corresponding to this 0.6 and 1, you will get that. So these graphs are there which will give you the different values. The coefficient of friction you will get corresponding to the 1 value of L by D ratio. 1 is somewhere here and 6 is here. So this will be the coefficient of friction F, and this from this F you will get F multiplied by W multiplied by R, that means the frictional torque, and then you will get the heat generation H gen. The flow rate you can find corresponding to this 0.6 and L by D ratio is equal to 1. You will have this flow rate, multiply this term, this number which you have obtained from RCNL, you will get the flow. So these are the way, and this is the Trumpler's design criteria. You have to check whether these all are satisfied or not. In this module of sliding contact bearing, we studied about a type of bearing which is very simple. There will be a journal and there will be a bushing or a bearing, and in between that will be the lubricant, and due to rotation of the shaft, pressure is self generated, and that is called the hydrodynamic pressure. And then we studied the mathematical modeling to get the pressure, and we studied different charts given by Raimondi and Boyd to get different performance parameters or the terms which decides whether the bearing is designed accurately or not. Thereafter, we also studied what is the effect of change of clearance on different performance parameters, and we also studied what should be the different values of minimum film thickness, the value of flow rate, the value of other performance parameters as per the Trumpler's and others. Thank you.